17. Evaluate the integral from minus infinity to 0 of x times e to the 2x dx, or show that it diverges. This is an improper integral, so divergence should be on the table as a possibility here for what's going on. This is a good crossover problem, just like the previous problem, number 16. It tests a lot of different things here because it's going to test both an improper integral, but the way we find the antiderivative here is actually going to be through integration by parts. So when we have the integral of x times e to the 2x, let's do that integration by parts. Our choices should say that polynomials is a better option, the exponential functions for our choice of u here. So u is x, du is dx, dv is e to the 2x dx, v is 1/2 e to the 2x. And so then, just looking at the antiderivative here, ignoring the bounds for the time being, x e to the 2x dx. So here is our u, here is our dv. And so this is, of course, equal to uv minus the integral of v du. And putting these pieces together here, we end up with x times 1/2 e to the 2x minus the integral of v, 1/2 e to the 2x du, which is dx. And so we have successfully reduced the exponent here. It was x times e to the 2x. Now it's just 1 times e to the 2x. I guess so 1/2, but we can always move that constant outside. So what do we have? 1/2 x e to the 2x minus, this will be, bring down another factor of 2 here in the denominator, 1/4 e to the 2x plus c. So this is our antiderivative. So now let's go ahead and pull in our bounds. And to pull in our bounds, of course, we're going to rewrite this as, this is really the limit as r goes to negative infinity of the integral from r to 0, x e to the 2x dx. What do we have? Limit as r goes to minus infinity. Let's use what we just found for our antiderivative here. 1/2 x e to the 2x minus 1/4 e to the 2x. Plug in r, plug in 0. And so this gives us the limit as r goes to minus infinity. Let's go ahead and plug in everything here. So when we plug in 0, we get 1/2 times 0. Well, times something, who cares? That will be a 0. Minus 1/4 e to the 2x. So that is going to be e to the 0. That's going to be 1. Minus, now we plop in r into all of this. Minus 1/2 r e to the 2r. Minus 1/4 e to the 2r. Okay, so now it's time to look to see what's going on with the limit here. Well, that's just a constant, just minus 1/4. We can move that outside the limit. When we take the limit as r goes to negative infinity of this term here, e to the minus 2r, that goes to 0 as r goes to minus infinity. And so this term is going to go to 0. So the only thing we have to really worry about is this 1/2 r e to the 2r term. So we have minus 1/4 minus 1/2 times the limit as r goes to minus infinity of r e to the 2r. Okay, so how do we handle this? This is an important enough important enough limit that I'm going to do on a separate sheet of paper. So as r goes to minus infinity, r goes to minus infinity, e to the 2r, we already said that goes to 0. So this is an infinity times 0 indeterminate form. So we should know that we have to use L'Hopital's rule to evaluate this limit, but it's going to be L'Hopital's rule after doing some manipulation here. And how we're going to manipulate, this is all a throwback to Calculus 1. This is a perfectly good Calculus 1 problem. So I'm going to leave r upstairs. Instead of multiplying by e to the 2r, I'm going to divide by e to the minus 2r. And so, what do we end up with? Now we have an infinity over infinity indeterminate form. As r goes to minus infinity, e to the minus 2r, that goes to infinity. So L'Hopital's rule, I guess I can put the standard L'Hopital comment there. So derivative of r with respect to r is 1. Derivative of e to the minus 2r with respect to r is negative 2 e to the minus 2r. So at this point then, we can go ahead and evaluate the limit. I mean, we want to move that back upstairs to make this more clear what's going on. That's not bad. But as r goes to minus infinity, e to the 2r goes to 0, this limit here is 0. So to bring back here, this ends up as minus 1/4 minus 1/2 times 0 is minus 1/4. So several things going on in this problem. The integration by parts in conjunction with the improper integral. And then I think a lot of people get tripped up on just how to evaluate this limit. You have to use L'Hopital's rule.